Hello everyone, I am Abhijit Lal, Assistant Professor, EEE Department, BIT Durg. Today we will study about half wave rectifier. The contents will be introduction, the circuit diagram of half wave rectifier, waveform of output voltage and current, analysis of various circuit parameters, then disadvantages of half wave rectifier. Now let us study what is half wave rectifier. A half wave rectifier converts an alternating current signal into a pulse direct current signal by allowing only one half of the waveform to pass. In half wave rectifier, the rectifying element conducts only during positive half cycle of the input AC supply. The negative cycles of AC are eliminated from the output. As we all know, in a AC signal there are two halves, that is positive half and negative half. So, as we have studied the basics of a rectifier, it is a device which converts AC signal or bidirectional current into unidirectional, or which is also called as DC. So, a rectifier is a device which converts AC into DC. So, half wave rectifier converts only one half of the AC into DC, and the another half will remain as it is, or it will not be shown in the output, or no output will be given for the another half. So, that is why it is called as half wave rectifier. Now, this picture shows the circuit diagram of half wave rectifier. In this, the rectifying element is the diode denoted by D. The resistance, forward resistance of the diode is denoted by RF. RL denotes the resistive load connected to the rectifying circuit, and the supply is given through a transformer. The transformer is used because we can give variable supply to the input side, and if we want to give only a constant supply, then transformer can be omitted, but in most of the cases the supply is given through a transformer, so that we can have a variable input supply, so that we can change the output according to our requirement. So, here the primary of the transformer is given with the AC supply according to the requirement. That voltage is in most of the cases it is a step down, then that the voltage occurring at the secondary of the transformer is given to the rectifying circuit, and it becomes the input to the diode, and from that the output will be obtained at the load side. Now, the above circuit consists of first the rectifying element, that is PN junction diode, second one is the source of AC voltage, and third is resistive load. Usually the rectifier circuits are operated from AC mains supply of frequency 50 Hz. To obtain the desired DC voltage across the load, the AC voltage is applied to rectifier circuit using suitable step up or step down transformer with necessary turns ratio. The transformer decides the peak value of the secondary voltage. So, if N1 is the number of turns in primary and N2 is the number of secondary turns, and F is the supply frequency and RF is the forward resistance of the diode, and let us denote EPM as the peak value of primary voltage, then N2 by N1 will be equal to ESM upon EPM, that is the voltage at the secondary divided by the voltage at the primary, where ESM is the peak value of the secondary AC voltage. Now, as the nature of ESM, that is secondary voltage of transformer, it is sinusoidal, then the instantaneous value will be given by small es equal to ESM sin omega t, where omega is equal to 2 pi f. Now, assume that under reverse bias condition the diode acts almost as open circuit, that is it is not conducting any current. So, the rectifier, in the half wave rectifier, a single diode is used in which the diode will conduct in the forward bias condition, and in the reverse bias condition when the negative half occurs, it acts as a reverse bias condition for the diode, and at that time diode almost acts as an open circuit and no current will flow through it. Now, let us study about the operation of half wave rectifier. During the positive half cycle of secondary AC voltage, terminal A becomes positive with respect to terminal B. So, referring to the diagram which we have seen about the half wave rectifier, or the circuit which we have seen about the half wave rectifier, when the positive half occurs, at that time the terminal A becomes positive and terminal B becomes negative. So, what happens at that time? the diode is forward biased and the current flows in the circuit in the clockwise direction as shown in the circuit diagram. The current will flow for almost full positive half cycle and through the load resistance RL, hence denoted as IL, the load current. So, for the positive half, when it acts as a forward biased condition for the diode, the current starts flowing through diode and it flows through the load resistance, and that current is called as the load current and it is denoted by IL. During negative half cycle, terminal A becomes negative with respect to terminal B, hence diode becomes reverse biased, hence no current flows in the circuit. The resultant circuit current, also called as load current, is in the form of half sinusoidal pulses. That means, we will get a half sinusoidal pulses for the positive half, and when the supply is negative, that means the negative direction of the supply comes, we will not get any output. So, in the output we will get discontinuous pulses of, or we can say that half sinusoidal pulses at the output. The load voltage is the product of load current and load resistance, hence it will also be in the form of half sinusoidal pulses. The different waveforms are shown below in the given figure. So, the load current and load voltage waveforms for half waves rectifier occurs like this. The first wave is showing the input supply, in which the AC wave is shown with positive half and negative half. The next figure shows about the load current. In this we can clearly see the time duration from 0 to pi when the forward bias condition is occurring for a diode. We are getting the load current similar to that of the input. That means, the output, although we are rectifying it from AC to DC, but we are getting some pulses, or we can say that ripples in the output. That is why it is not pure DC. It is again shown as a sinusoidal, but half sinusoidal wave. And for the cycle, that is for the time period pi to 2 pi, when negative pulse is occurring in the supply, it acts as a reverse bias condition for the diode, and at that time diode is acting as an open circuit and no load current will occur at the output. So, no wave will be shown at the output for pi to 2 pi. So, the load current will be 0 for the duration pi to 2 pi, and similarly the waveforms will be shown for the load voltage, because we are dealing here with a resistive load. So, the current and voltage remains in the same phase. So, the waveform obtained will be the similar to that of the load current also. The DC output waveform is expected to be a straight line, but the half wave rectifier gives output in the form of positive sinusoidal pulses. Hence, the output is called pulsating DC and it is discontinuous in nature. Since the output is discontinuous, therefore, it is necessary to calculate the average value of load current and output voltage. So, let us study about the average DC load current. So, how we can find the value for the load current. So, mathematically, current waveform can be described as IL is equal to Im sin omega t for the duration 0 to pi. That means, as we have seen in the waveforms, for the duration 0 to pi we are getting output for the load current. So, the current will be defined for that duration only, that is for 0 to pi. Here the current IL is equal to Im sin omega t. Now, for the duration pi to 2 pi, when the diode is under reverse bias condition, it is acting as a open circuit. So, at that time no load current will flow. So, the value of IL will be 0. Here the Im represents the peak value of load current. So, the average DC load current will be equal to IDC and its numerical value will be equal to 1 upon 2 pi integration 0 to 2 pi IL d omega t. From here we can see it will be equal to 1 upon 2 pi integration 0 to 2 pi Im sin omega t d of omega t. As no current flows during negative half cycle of AC voltage, that is between omega t equal to pi to 2 pi, therefore, new limits will be used, that is IDC will be equal to 1 upon 2 pi, that is we will find the average value from 0 to pi, and the final value obtained will be Im upon pi, which will be the average value of load current. So, applying the Kirchhoff's voltage law, we can write the value of Im as ESM upon Rf plus RL plus Rs. Here Rs is resistance of secondary winding of transformer and can be neglected if value is not given. Now, let us find the value for average DC load voltage. It is denoted by EDC. So, it is a product of average DC load current and the load resistance RL. So, EDC, that is the average DC load voltage, will be equal to IDC into RL. So, its value will be equal to Im upon pi into RL, or which is equal to ESM upon Rf plus RL plus Rs into pi, the whole multiplication by RL. So, the winding resistance Rs and forward diode resistance Rf are practically very small compared to RL. Hence, EDC will be equal to ESM upon pi multiplied by Rf plus Rs divided by RL plus 1. But as Rf and Rs are small compared to RL, therefore, Rf plus Rs divided by RL is negligibly small compared to 1. So, it can be neglected. So, the final value of, or we can say that the approximate value of EDC will be equal to ESM upon pi. Now, the RMS value of load current, it is denoted by IRMS. So, the RMS means the squaring and finding the mean and then finding the square root. Hence, the RMS value of the load current can be obtained as IRMS equal to square root of 1 upon 2 pi integration 0 to pi, then Im sin omega t the whole square d omega t. So, the value will be equal to Im upon 2. Next is the DC power output. It is denoted by PDC. So, the DC power output can be obtained as PDC equal to EDC into IDC. Now, here the DC power output is nothing but the power which we are getting at the load side. It is obtained from the average value of voltage and current. So, here the multiplication of average voltage and average current is used. From that we can find the DC output power, or we can also use the formula that is I square DC into RL. So, from here we can obtain the DC power output as I square DC into RL, and as we all know, we have found IDC is equal to Im upon pi. So, Im upon pi the whole square into RL, and it will be Im square upon pi square into RL. Here Im is equal to ESM upon Rf plus RL plus Rs. The final value for PDC will be equal to ESM square into RL divided by pi square multiplied by Rf plus RL plus Rs the whole square. Now, let us find out the value for the AC power input, which is PAC. So, the input is given in the rectifier circuit through a transformer. So, the AC power input will be the input given in the primary side of the transformer. So, the power input taken from the secondary of transformer is the power supplied to the resistances, that is, we have seen in the circuit the main supply is given to the primary of the transformer, but stepped up or stepped down according to the requirement. So, the value obtained at the secondary of the transformer will be given to the rectifier circuit, or we can say that the rectifying element, which is a diode. So, that will give us the actual value of the AC power input. So, here we have to find the AC power input of the rectifying element. So, the power is supplied to the three resistances, that is the load resistance RL, diode resistance RF, and winding resistance RS. So, the AC power is given by PAC equal to I square RMS into RL plus RF plus RS. So, this formula is obtained from the formula of power, that is I square R. So, here the current which we are taking, since we are finding the power in the form of AC, so the current which we are taking is the RMS current. So, the current will be I square RMS, and multiplied by the resistance. So, here the resistances are the summation of RL plus RF plus RS. Now, here the value of IRMS we have already found out, which came to be Im by 2 for half wave rectifier. So, the final value of AC power input will be Im square upon 4 multiplied by RL plus RF plus RS. Now, the most important factor of the half wave rectifier is the rectifier efficiency. So, the rectifier efficiency shows the value of conversion, or you can say that how efficient the rectifier is in converting AC to DC. So, the rectifier efficiency will tell the amount of rectification done from AC to DC, and it is defined as the ratio of output DC power to input AC power. So, the two values which we have found out, from that we can obtain the value of rectifier efficiency. So, efficiency is equal to DC output power divided by AC input power, that is PDC divided by PAC. So, on putting the values of the DC output power and the DC input power, which we have already calculated, the efficiency will be equal to, on solving we will get 0.406 divided by 1 plus RF plus RS divided by RL. Now, in the denominator, if RF plus RS, here this both the summation of the value of RF plus RS is very small compared to RL, which we have already studied. The forward resistance and the resistance of the secondary winding of the transformer, it is very less compared to the load resistance as mentioned earlier. So, we get maximum theoretical efficiency of half wave rectifier, that is percentage efficiency will be equal to 0.406 multiplied by 100, and it comes up to be 40.6%. Therefore, maximum 40.6% of AC power gets converted into DC power in the load in half wave rectifier, which means that if we are giving AC power in the input to the half wave rectifier, only 40.6% of the AC power gets converted into DC power, which defines the efficiency of the rectifier. So, if 40% is the efficiency of half wave rectifier, then remaining 60% will be present in terms of ripples in the output, and this we have seen in the waveform also. The waveform obtained is not pure DC, it contains the ripples. So, as the efficiency tells that 40% is the conversion of AC to DC. So, the remaining 60% will be the ripples in the output. Therefore, more the efficiency, less will be the ripples. So, if we use some means to remove the ripples, so from that the efficiency of the rectifier will be increased. Now, the next important parameter which should be calculated for the analysis of half wave rectifier is ripple factor. It is denoted by gamma. It is defined as the ratio of RMS value of the AC component to the average or DC component. That means, the ripple factor shows or we can say that it is defined as the ratio of RMS value. That means, the RMS value of AC component which is obtained at the output divided by the average or the DC component of the output, that will give us the ripple factor. So, as the output of half wave rectifier is not pure DC, it is not pure DC, but a pulsating DC, where the pulsating components are called as ripples. So, ideally there should be no ripple in the rectifier output. So, if we talk about the ideal rectifier, it should give a pure DC at the output, that means a straight line in the output, but as we have seen in the waveform, the output obtained is in the form of sinusoidal, half sinusoidal wave, that means it contains the ripples. So, in practical case, the output will be containing the ripples and it will be in the form of sinusoidal. So, ripple factor measures the amount of ripples in the output. That is why the ripple factor is necessary to calculate to find out the amount of ripples present in the output. So, the ripple factor tells how successful the rectifier circuit is to obtain pure DC from AC input. So, here the ripple factor will be equal to the ratio of RMS value of the AC component divided by average or DC component. So, it will give the value of the ripples present in the output. So, the value of gamma in half wave rectifier is 1.211, which indicates that the ripple contents in the output are 1.211 times the DC component, that is 121.1% of DC component. This can be understood like this. In half wave rectifier we are getting the value of ripple factor as 1.211. So, the ripples which are present in the output, that means the AC component, we can say that the AC component which is called as ripples, it is 121.1% times of the DC component. That is why the efficiency is below 50%, which we have obtained in the last topic only. So, that is why the efficiency is very less for half wave rectifier. So, the ripple factor for half wave rectifier is very high, which indicates that the half wave rectifier is a poor converter of AC to DC. So, since the AC component or the ripple component is more than the DC component, which is our need, that is why we can say that the half wave rectifier is a poor converter of AC to DC. So, the ripple factor is minimized using filter circuits along with the rectifiers. So, the next expression will be for the load current IL. The load current IL is composed of AC and DC components and can be expressed using Fourier series as follows. That is, IL is equal to Im in bracket 1 by pi plus 1 upon 2 into sin omega t minus 2 upon 3 pi cos 2 omega t, etc. So, the above expression shows that the current may be considered to be the sum of an infinite number of current components. So, in the figure we can say that the load current comprises of a number of infinite current components. So, in the above expression for current, the first term is the average or DC value of the load current. Second term is a varying component, that is it is changing with respect to frequency, that is omega, it depends upon the value of omega. So, it is a varying component having frequency same as that of AC supply voltage. This is called the fundamental component. Now, the third term is again a varying component having frequency twice the frequency of supply voltage. This is called second harmonic component. Similarly, all other terms represents the AC components and are called harmonics. So, first term will be the DC value of the load current, second is the fundamental component, and after that all the components are the harmonic components. Thus, ripple in the output is due to the fundamental component along with the various harmonic components. So, the average value of the total pulsating DC is the DC value of the load current given by the constant terms in the series, that is Im upon pi. Now, the next important factor is the peak inverse voltage, which is also called as PIV. As we have already studied about the PIV, which is called as peak inverse voltage, it is the amount of voltage applied across a diode when it is in a reverse bias condition, or we can say that when the supply voltage is in the reverse direction. So, the peak inverse voltage is the peak voltage across the diode in the reverse direction, that is when the diode is reverse biased. So, in half wave rectifier, the load current is ideally 0 when the diode is reverse biased, and hence the maximum value of the voltage that can exist across the diode is nothing but ESM, which means that the voltage occurring at the secondary of the transformer, which is occurring at the diode at the reverse bias condition, that means for the negative half of the supply, the maximum value of that will be the PIV. That means that will be the maximum voltage which will act across the diode at the reverse bias condition. So, PIV of diode is equal to ESM, and it is equal to maximum value of secondary voltage, which is equal to pi EDC when IDC is equal to 0. This is called PIV rating of diode. So, from this again PIV is a rating of a diode from other ratings, that is its rated current, rated voltage. PIV is also a rating given for the diode, in which it is defined that this will be the maximum voltage which can be applied across a diode during the reverse bias condition, and if the voltage exceeds the PIV in the reverse bias direction, that means above the PIV, it can damage the diode. The next factor is the transformer utilization factor, denoted as TUF. So, this factor indicates the amount of utilization of the transformer in the circuit. As we have seen in the circuit of the half wave rectifier, the supply is not directly given to the diode, but it is given through a transformer. So, a factor called as transformer utilization factor is calculated to find out the amount of utilization of the transformer in the rectifier circuit. So, it is defined as the ratio of DC power delivered to the load to the AC power rating of the transformer. That means, the ratio of the DC power delivered, that means the power obtaining at the output divided by the AC power rating of the transformer, power rating of the secondary side of the transformer. So, the secondary voltage is purely sinusoidal, hence its RMS value is 1 upon root 2 time the maximum value, while the current is half sinusoidal, hence its RMS value is half of the maximum value. So, by using these values we can find out the transformer utilization factor for the half wave rectifier. So, this expression shows the value for the TUF, that is the ratio of DC power delivered to the load divided by the AC power rating of the transformer. So, in numerator the DC power delivered will be Im upon pi the whole square multiplied by RL divided by ESM into Im divided by 2 into root 2. So, neglecting the drop across RF and RS, we can write ESM is equal to Im into RL. So, TUF will be, that is the transformer utilization factor will be 0.287. So, the value of transformer utilization factor is low, which shows that in half wave rectifier the transformer is not fully utilized. So, this can be compared with the value of rectifier efficiency also, and as well as the value of ripple factor also. As we have seen, the efficiency is around the 40%. From that we can conclude that the half wave rectifier is a poor converter of AC to DC, and from the value of ripple factor we have seen that the AC component, that is the ripples, the amount of ripple is 121.1% more than that of the DC component. That means, at the output we are getting the more AC component than the DC component. So, similarly with this TUF, the value of TUF is around 0.287. This shows that the transformer is not fully utilized. That means, the output of the transformer is given to the rectifier circuit, it is not fully converted to the DC. Now, let us discuss the disadvantages of half wave rectifier. So, the first disadvantage is the ripple factor of half wave rectifier circuit is 1.21, that which is quite high. The output contains lot of varying components. That means, the amount of voltage to be converted from AC to DC is very less. That means, the conversion process is very poor. Next disadvantage is the maximum theoretical rectification efficiency is found to be 40%. The practical value will be less than this. This indicates that half wave rectifier circuit is quite inefficient. We have seen in the topic of rectification efficiency, the efficiency was rectifier efficiency in the efficiency was 40%, around 40%, which we have calculated, but when we practically apply it, the value can be less than the 40% also. So, this shows that the half wave rectifier is not very much efficient for the conversion of AC to DC. The third disadvantage is The circuit has low transformer utilization factor, showing that the transformer is not fully utilized. As we have seen, the value obtained for TUF is 0.287. This shows that the transformer which is used for the rectification is not fully utilized. That means the output obtained from the transformer, that is the AC which is obtained, is not fully converted to the DC. And the last, the disadvantage is the DC current is flowing through the secondary winding of the transformer, which may cause a DC saturation of the core of the transformer. So, to minimize the saturation, the transformer size has to be increased accordingly. This increases the cost. So, this is another drawback for the half wave rectifier. In this, DC current also flows through the circuit, the secondary side of the transformer, which increases the saturation level. So, in order to to reduce the saturation level, the size of the transformer should be increased, but that unnecessarily increases the cost of the transformer. So, these are all the disadvantages of half wave rectifier. So, we have studied about the circuit of half wave rectifier. We have seen the waveforms obtained for the half wave rectifier, that means the waveform for the output voltage and output current. There we have seen that it contains a ripple. We will not obtain the full DC or a straight line DC at the output. It contains some ripples. So, the output will be in the form of sinusoidal wave, that is half sinusoidal wave. Then after that, we have seen the calculation of various parameters, that is load current, load voltage, transformer utilization factor, ripple factor, rectifier efficiency, etc. And finally, we have discussed about the disadvantages of half wave rectifier. So, in the coming classes, we will discuss about the full wave rectifier, both the configuration, that is center type bridge rectifier, which will definitely overcome the disadvantages of half wave rectifier. Thank you.